For number 15, we're going to look at examples and decide if they're independent or dependent. Events are independent if when one happens, it has no effect at all on the probability of the other happening. So for A, we have a person attains a position as a professor and the same person attaining a PhD. So these are going to be dependent because when F happens, when someone has a PhD, they are much more likely to get a position as a professor. The probability goes up of getting a professor job when you have a PhD. For B, a randomly selected person having a high GPA, another randomly selected person having a low GPA. These cannot affect each other because the people are randomly selected, so the events are totally independent. For C, the unusually foggy weather in London on May 8th, and F, the number of car accidents in London on May 8th. These will definitely be dependent because foggy weather will definitely have an effect on the number of car accidents. For number 16, we are told that events E and F are independent, and we're asked to find the AND probability, the probability that they both happen. And when events are independent, you can figure that out just by multiplying together their individual probabilities. So to find probability of E and F, we take 0.7 times 0.8 and get 0.56. Now if the events are not independent, you need conditional probabilities in order to figure out an AND probability. So only multiply together the two probabilities if you know that they're independent. For number 17, we're finding the probability of getting 4 tails in a row when we flip a coin. And each coin flip is independent. The previous coin flip has absolutely no effect on the probability of the next flip. The chances of a tail is always 50%, heads is always 50%. So to figure out the probability of tails and tails and tails and tails 4 times in a row, you can just multiply the probability of each event. So there's the first tail, multiplied by the chance of getting tails again, multiplied by the chance of getting a third tail, multiplied by the chance of getting our fourth tail. And so we get a 0.0625 chance of getting 4 tails in a row. So let's interpret that result. Each time you flip a coin 4 times in a row, you have a 6% chance of getting tails, 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 tails. So if you kept doing 4 flips in a row, and then another 4 flips in a row, and then another, if you did it 100 times, a 6% chance means that 6 out of those 100 would probably be 4 tails in a row. For number 18, we're told 6% of the population of a large country is hopelessly romantic, and we're going to randomly select 2 people. And what's the probability that they are both hopelessly romantic? So these are independent events. The first selection and the second selection are both independent. Doesn't matter who we pick first, the chances that the second person is hopelessly romantic is still 6%. So the chances the first person was hopelessly romantic is 0.06, and if we want to know the chances that they both are, we multiply the probability of both events together. They both have a 6% chance. So the probability that they're both hopelessly romantic is 0.0036. And for part B, the probability that at least one person is hopelessly romantic, it's easiest to do part B using the complement rule. So let's figure out the probability that nobody is hopelessly romantic. Out of the 2 people we picked, neither one is hopelessly romantic. So if 6% is, that means there's a 94% chance that the first person isn't hopelessly romantic. And since these events are independent, we're randomly selecting a second person, we can multiply the chances that they also are not hopelessly romantic. So 88.36% of the time, both people will not be hopelessly romantic. So all the rest of the time, at least one of them will be. Either they both will, or the first person will, or the second person will. So here's the chances nobody is. If we do 1 minus 0.8836, we'll get the chances that at least one person is. So the complement rule there. For number 19, we're giving information about a certain test. And for part A says, what is the probability that the test comes back negative for all 6 people? And we've chosen 6 randomly selected people, and they do not have the antibody, which the problem says 99.6% of the time this test is effective. And since they don't have the antibody, it should be coming back negative. That's the correct response, and the test will do it 99.6% of the time. And all these people are independent because they were randomly selected. So we can just multiply each individual chances of having the correct test together. So multiply 99.6 together 6 times. So I've done it twice. Type it a 3rd time in the calculator, 4th time, 5th, and the 6th time. And when you round, you'll get 0.9762. And for part B, we can use the complement rule. Part B is asking what's the chances of at least one positive. So out of the 6 people, there could be 1 positive response, it could be 2, it could be 3, 4, 5, or all 6. But at least 1 is going to be positive. Well, in part A, we found the chances that there are 0 positives, that all of them came back negative. So if this percent of the time there are 0 positives, then all the rest of the time there has to be at least 1 positive. So if we do 1 minus the chances of 0 positives, we're left with the chances that there's at least 1 positive. And for 20, we're again looking at independent events. George loses 87% of all staring contests. So no matter what happened on the previous staring contest, the next time he'll still have an 87% chance of losing. So independent events. So what's the probability that George loses 2 staring contests in a row? Since the events are independent, you just take the chances of losing the first contest and multiply by the chances of losing the second. And here's the probability of losing 2 in a row. The probability that George loses 3 in a row, we would just multiply by a 3rd staring contest, this 87% chance of losing. And so George has this probability chance of losing 3 staring contests in a row.